Now we're going to look at something called mechanical energy. We've discussed kinetic energy, we've discussed potential energy. Mechanical energy is a combination between potential energy and kinetic energy. So often people forget about it because it doesn't have a formula really of its own. It's just about adding two different types of energy that we already know. So we know potential energy is mgh, and we know kinetic energy is a half mv squared. This is true. Now, you're going to use this when you are dealing with non-linear motion. The minute you have something that is like a roller coaster or something swinging or something like that, those are not straight lines. Equations of motion can only be used for straight lines. However, if you've got a thing that is changing its height in some way on a non-direct path, then you can start to use mechanical energy. So the mechanical energy is going to remain constant because energy we do know is conserved. So the potential energy that an object had, let's say at A, will turn into kinetic energy at B. In other words, it will move. And at the top of the projectile, it will become potential energy again. When a pendulum, think of this as a pendulum, it swings, it stops. That's no kinetic energy. It swings, it stops. No kinetic energy. Swings, stops. No kinetic energy. In the middle here, all its potential energy has been lost to kinetic energy. So, this is the fastest part of the motion. Swing, stop. Swing, stop. This is fast, maximum kinetic energy. This is zero kinetic energy. This is zero kinetic energy. This is slow, but it's high, maximum potential energy. Here, maximum potential energy. Notice that it rises to the same height. Potential converted to kinetic, kinetic converted to potential. What about if we were at some random point over here called D, then part of the energy would be kinetic and part would be potential. What's interesting to note is that potential plus kinetic is always a constant. So energy cannot be created nor destroyed. It can only be converted from one form to another. So that restated is total energy in a closed system remains constant, and it is the conservation of energy. These are statements of the conservation of energy. So let's look at an example. A pendulum has a mass of 800 grams. It swings to a maximum height of 50 centimeters. What is its maximum potential energy? We know what potential energy is. It's mgh. So we change mass 0,8. G, this is on 10, but you should really use 9.8. But because this is easier to work with than 10, let's just stay with 10. So 10 is G, and H is 50 centimeters converted into meters. Notice I had to convert the 800 grams into kilograms as well. So divide by 100 over here, divide by 1,000 over there. And I get 4 joules. That is the maximum potential energy at the top of the swing because of the height. Now, as it comes down and swings through and comes through the bottom over there, all of that potential energy becomes kinetic energy. So the kinetic energy will be 4 joules. Kinetic energy is 4 joules. The mass is 0,8. Half mv squared, you square root, and you've got plus minus 3,16 meters per second. What does that plus minus mean? That plus minus means that it could either be going up towards the right or it could be going up towards the left as it moves backwards and forwards and backwards and forwards. Now they want to know, what is the velocity of the pendulum when it reached only 30 centimeters? Now, first thing to notice is that this kinetic energy at the bottom is the mechanical energy, which also was the potential energy at the top, was also mechanical energy. Why? Because the kinetic energy here was equal to 0. And the potential energy here was equal to 0. So this 4 joules is my total mechanical energy, which is the kinetic plus potential. I put the 4 in. I now have a height of 30 centimeters. I convert that into meters, and I go 4 is equal to a half 0,8 v squared That's the kinetic energy portion, plus mgh, but I only use 30 centimeters, not 50, and I find that that V turns out to be plus or minus 2 meters per second. Again, in your equations now, you'll use 9.8, but this whole question worked out very nicely using 10, so I've left it like that.